We have a uniform cylindrical turntable of radius 1.8 meters and mass 26.1 kilograms, and it's rotating counterclockwise, so in the positive direction, in a horizontal plane, and it has an initial angular speed of 4 pi radians per second. The fixed turntable bearing is frictionless, so it has a bearing, right? So kind of think of like a record player, right? It has something in the middle here, and then you have it rotating around the bearing, so that bearing is causing it to rotate, and that bearing is also the axis of rotation. Good so far? And it's frictionless, so it is not causing the turntable to slow down. So it doesn't have any torque working in the opposite direction. Now we have a lump of clay that's 2.39 kilograms. It's going to be dropped onto the turntable. Now if it's dropped, what's its initial velocity? If it's dropped, the initial velocity is 0. So it's going to be dropped from a small distance, and then it's going to immediately stick to the turntable at 1.7 meters to the east. They give us the moment of inertia equation for the disk, and you should know that for any point mass, it's always mr squared. All right. So what we're going to do first is we're going to find both moments of inertia of the turntable. So initially, what we have is our turntable here, and we have a clay above it. And what do I know about this piece of clay right now? It's at 0 velocity. It's at rest. Okay. Now it's not on the turntable. So if I'm talking about the moment of inertia of the turntable as it is currently spinning, the moment of inertia is just the turntable. Make sense? So that means my initial moment of inertia is the inertia of only the turntable. I of the clay equals 0 since not moving on the turntable. All right, so it's not on the turntable, it's not moving, it's not affecting the moment of inertia. So the turntable is a disk, so that's going to be 1/2. The mass is 1.8 meters. Oops, that's the radius. The mass is 26.1 kilograms. So 26.1 kilograms. And the radius is 1.8 meters, quantity squared. And so if you plug and chug all that, you end up getting 42.3 kilograms times meter squared. So this is our initial moment of inertia of the turntable. Okay. Then what happens is the clay falls and sticks to the turntable. So now it's right here. So here's our clay after. And so our final moment of inertia is the turntable, but it's also the moment of inertia of the clay. Now, what do we call the clay on here? What type of inertia is that? Yep, point mass, good. I've got some lip reading skills going on here. Everyone's so nervous. They don't want to say it out loud, right? So here, we're going to get, for the turntable, we found that already, 42.3 kilograms times meter squared, plus, for a point mass, it's mr squared. So this is going to be the mass, it's going to be 2.39 kilograms. And then the r here, it is not going to be the same as the r here. So the radius of the disk is 1.8 meters, but we need to figure out this point mass, how far away it is from the bearing, so from that axis of rotation. And here it's going to be 1.7 meters. So 1.7 meters, square that guy. So the final moment of inertia after the clay sticks ends up being 49.2 kilograms times meter squared. Why is the angular momentum conserved when the clay hits the turntable? The external net torque is 0. Excellent. External net torque, good job, equals 0. Okay? The clay, when it hits, it's not creating a torque to make this turntable spin, right? So what's happening is it's falling on. So if I have my turntable here, not perfect here, but if it's falling, right, it's going downward. It's not causing this to spin this way. The turntable is spinning this way, but the clay is not creating an external torque or anything. Okay, so we're good here. So in this, so the external net torque in the clay wheel system is going to be 0. All right, so we have our initial angular momentum has to equal the final angular momentum. So if we are looking for the angular speed, that's perfect that we've identified this relationship, because once you know this is true, now we can use this relationship to set up and solve anything we're missing. And in this case, we're trying to find the final angular speed. So I know that I initial omega initial has to equal I final omega final, and we're trying to find this final angular speed. So I initial is 42.3 kilograms times meter squared. They tell us the initial speed was 4 pi radians per second, and that equals the final moment of inertia was 49.2 kilograms times meter squared times the final angular velocity. Now, what do we know about the final angular velocity for this situation? Before we calculate it, what do we know about it? It's got to be, so what happened to our moment of inertia? It increased, so this would have to decrease. Good. It would be less. So we get the final angular velocity is going to be, if you divide both sides by 49.2, you get 10.8 radians per second. This is moving counterclockwise, so it stays positive. So let's compare the initial and final speeds. So we have the initial angular velocity was 4 pi radians per second, which is approximately 12.6 radians per second, right? The final angular velocity was 10.8 radians per second. All right, now the reason again why we knew this was the case was because our moment of inertia increased in the collision. Okay, because the moment of inertia is increasing because the angular velocity, or the angular momentum, because it's conserved, then the speed is going to have to change to accommodate. So an increase in momentum is going to be a decrease in speed. So here we have the final angular speed is less because the moment of inertia increased. And again, not just that it increased, the moment of inertia increased, but also because we know that the angular momentum is conserved. If the angular momentum is not conserved, we cannot state this relationship in this manner. All right. What about internal energy? Do we have any change in energy? Do you guys remember the relationships from example 1? What do we know about kinetic energy with respect to angular velocity? What type of a relationship? Inverse or direct? Direct, good. And then what about with moment of inertia? Inverse or direct relationship? Inverse. Okay, so here's the thing, let's take a look. The angular speed decreased. Oops. So the angular speed decreased, so kinetic energy must also decrease. It's a direct relationship. If one goes down, the other goes down. All right. If we didn't know the angular speed, we can also look at the inertia. Here, the inertia, the moment of inertia increased, but this is an inverse relationship. So if this increases, then we know that we must be losing energy. So we're losing kinetic energy. You do not need to have both. I'm just putting both of them because you need to understand both situations. Okay, again, if we were going to make these relationships, you would have to go through and derive just like we did in example 1 and show why that's true. All right, so let's go ahead and find delta K. So delta K equals K final minus K initial. So K final, it's 1/2. The inertia for final was 49.2 kilograms times meter squared. The final velocity is 10.8 radians per second, quantity squared, minus 1/2, 42.3 kilograms times meter squared, and the velocity was 4 pi radians per second, quantity squared. And when you plug and chug all that in, you end up with the change in kinetic energy is negative 470.5 joules. Okay, so again, we know that we're losing energy in this situation.